Hi, welcome to our demonstration video for the open source leg for the IROS workshop, State of the Art in Robotic Leg Prostheses, Where We Are and Where We Want to Be. I'm Elliot Rouse. I'm an assistant professor at the University of Michigan, where I direct the Neurobionics lab. And this work will be co-presented with Dr. Alejandro Azacar, a former PhD student in my research group, now working with Google X, and Eunhee Lee, a current senior PhD student in my research group. I'd like to begin by sharing a little bit about the motivation for the open source leg project, the goal of which is really to lower the barrier for studying some of the control challenges that have hindered the widespread clinical adoption of these systems. Our idea is to create a common hardware platform that facilitates comparison of different control strategies from different research groups around the world, and also to lower the time and financial burden associated with the continual redevelopment of robotic legs before studying different control strategies. The purposes of their demonstration video is to showcase the open source leg and how to use it in a research setting, highlight our mechatronic implementation and software tools needed, showcase control demonstrations and also testing with human subjects. And the data for the human subject testing is openly available on the project's website, opensourceleg.com.
For this video, I will give a brief introduction of the open source leg and go through the setup required for running the leg. In this demonstration, we will assume the assembly of the open source leg is completed. The setup includes a laptop, a small board computer, which we use the Raspberry Pi, and the OSL. To clarify, the Pi is fully controlling the OSL, while the laptop is just being used for interfacing with the Pi. In this slide, I will briefly go through how to set up the Raspberry Pi for operating the OSL. First, we would need an image file which includes the operating system of the Pi. We provide the image file on the OSL website, which includes the operating system and necessary software packages so that people can start using the Pi right out of the box. This includes IP address emailer and access point, which is essential for accessing the Pi from a different workstation. IP address of the Pi will be sent to your email upon booting up the device. The demonstration of connecting the Pi using the IP address will be shown in the following slide. Access point, which uses fixed IP address, allows to access the Pi when there is no Wi-Fi available, and transition to the access point mode happens automatically when Wi-Fi connection is not established. The image also includes essential Python libraries and libraries for peripherals for data acquisition. And we also provide example codes and the Pi actuator software package for ease of use. Raspberry Pi allows the system to be fully portable, and in actual human subject testing, this can be attached to the human body or miniaturized and included within the designated location of the knee prosthesis. The entire control system was included and implemented in the Pi for controlling the OSL. Now, let me give you a simple demonstration of how we can interface into the Pi and control the OSL. First, we SSH into the Pi given the IP address of it. This is the equivalent process of directly connecting the Pi to a monitor. After typing the password, we can see that we're currently inside of the Pi. Next, we navigate into the folder which has controller which actuates the OSL. The Pi is executing an open loop voltage control, which does a homing routine, mapping the motor angle to the joint angle of the OSL for each joint, knee, and ankle. For the remainder, I'll explain the key components and recent changes in the design of OSL. In the OSL, we have two single-axis joints, which has a range of motion of 120 degrees and 30 degrees for knee and ankle joints, respectively. The knee has three-stage belt transmission, while the ankle has four-bar linkage transmission. After the transmission, the instantaneous peak torque of the knee joint is 150 Nm, and the peak torque of the ankle joint is 178 Nm. We have two motors on each joint, one at the knee and another at the ankle. The special thing about these motors is that they are drone motors, which are flat and wide compared to other brushless motors. These motor types allow us to provide high torque density, which is suitable for lightweight robotic systems, like wearable robots. This is the battery compartment of the leg, which has 4 cells, a total nominal voltage of 29.6 volt for each joint. The original batteries we have been using are discontinued, so we're recently enlarged the battery compartment size to accommodate different batteries. In terms of the sensors, there are IMU included in the Defy actuator package, and externally, you can add sensors such as torque sensors to the system, and these sensors can be detached from the OSL depending on each user's need, which demonstrates the scalability of the system.
In this portion of the video, I'll talk about the ways we control the open source leg. We typically use leg in position, current, or impedance control. To quantify the performance of the position controller, we ran frequency response tests seen here. The knee and ankle joints each commanded position trajectories composed of filtered Gaussian white noise scaled to plus or minus 5, 10, and 15 degree amplitudes. Using non-parametric system identification techniques, we constructed Bode plots of each joint and found a position bandwidth of 11 to 20 Hz. This bandwidth is higher than other prostheses and approximately 5 times higher than the human body, meaning that the open source leg is capable of tracking motions in the relevant frequencies of walking. We do much of our work with impedance control, where each joint is commanding the dynamics of a spring mass damper. That is, the desired torque at each joint is a function of 3 impedance parameters: stiffness, equilibrium angle, and damping, as well as position and velocity of each joint. In this video, you can see the knee joint switching between different impedance parameters. As equilibrium angle changes, so does knee angle, and as stiffness and damping change, the resulting oscillations and dynamics change as well. It is important to note that this impedance controller is actually built on top of the leg's current controller, so the leg is actually commanding a desired current instead of a desired torque. To enable walking, we use a finite state machine that progresses through 4 states: early stance, late stance, early swing, and late swing. Early stance is triggered by thresholds in the leg's normal force and the knee angle. The normal force is measured by the 6-axis load cell. The transition from early to late stance is triggered by a force threshold as well as a minimum amount of time in early stance. Transitioning into early swing occurs with another force threshold, and finally, the transition from early to late swing occurs with a threshold in knee angle as well as knee velocity. This results in 24 impedance parameters and 7 transition parameters that need to be tuned for the open source leg. To simplify this process, we weight normalize as many of these parameters as possible. This is what our state machine looks like in code. First, we enumerate the states of the gate cycle and include an unspecified state. Second, we initialize the vectors of impedance gains corresponding to each of the states. For example, you can see the knee stiffness gains for each state on line 47. Finally, we initialize the transition thresholds for each state. For example, lines 57 and 58 show that the transition to late swing requires a knee angle of at least 60 degrees and a knee velocity below 3 degrees per second. Here we can see the entire state machine logic. In essence, this code uses the transition criteria mentioned before to transition into early stance, early swing, late swing, and back into early stance. Once a state has been selected, the impedance gains for each joint are pulled from their respective vectors and sent to the open source leg. Here are some videos of what the tuning process looks like. In this first video, we simplified the state machine to only have stance and swing states. In the second video, we see a poorly tuned state machine that allows for some walking on the knee. Finally, after careful tuning of all impedance and transition parameters, the leg is capable of recreating human-like walking. Note that we always test new controllers on able-bodied subjects first, and we use an adapter that locks the knee back to simulate an amputation. Using the same state machine, with minor additional tuning, we can also generate realistic and meaningful walking patterns on patients with amputations. Here's a video of our lab's first patient walking with the leg after about 30 minutes of tuning. Our collaborators at the Shirley Ryan Ability Lab have tested the open source leg through various activities, including walking on level ground, ramps, and stairs. They also use an impedance controller as well as machine learning to transition between states and activities. More information on these controllers, as well as an open source dataset of sensor data and control parameters, are available in our recently published paper and on opensourceleg.com. Thank you.
Now we'll tell you a little bit about the open source leg website. The project's website, opensourceleg.com, has everything someone would need to build their own open source leg, including quotes, bill of materials, detailed assembly instructions, detailed control instructions, sample emails and vendor information, and then information about the Raspberry Pi, the image needed to get up and running, as well as open source data that can be downloaded from the website. And finally, in conclusion, I wanted to take a moment and thank you for watching our video on the demonstration of the open source robotic leg. And if you studied the control of robotic prostheses, I hope you will keep this project in mind in the future. The intent of this project was to create a community, and I'm excited to say we have 8 institutions around the country and around the world currently utilizing the open source robotic leg. Ultimately, we hope that this research will translate into improvements in the quality of life for individuals with disabilities. Thank you.